Alright, so this is the last problem from chapter 3 that I'll record, unless there's some that are particularly difficult that I get some requests for. And so this one is starting to look at two genes at the same time. So this is going to be just a straightforward example of how to do a dihybrid cross. And I know that going in, but you can sort of figure that out as you go with the problem. So in cats, curled ears result from an allele CU equals curled. And little cu equals normal. So these are the ears. Black color results from an independently assorting allele. Independently assorting allele. So that's really important that it's independently assorting. And so in this case we have G is black and little g is gray. So those are our two genes and our two alleles. One thing that's worth pointing out here is that gene symbols don't always have to be one letter. And it can get confusing when you start to have two letters. But just consider this as just one letter together. C and U always go together. I've seen people actually try to segregate the C and the U away from each other, just because you're used to using one letter for genotypes. And if you really wanted to, you could change this to just a big C and a little c. That would be fine. But you'll find that when we started even looking at some Drosophila genetics and those sorts of things, you can have 3 or 4 letters for a symbol. But there's nothing wrong with that. So now we're going to take a gray cat, homozygous for curled ears. All right, so it's homozygous for curled ears, so it's CU, and it has, so let's say, so where'd it go? So a gray cat, homozygous for curled ears, so it's gray. So if it's gray, it's got to be little g. And we're going to mate that with a homozygous black cat with normal ears. Homozygous black, G with normal ears, little cu. So it looks a little different now that we've got that going on. Then what do they want to know? All the we already know all the F1s are black and curled ears. So black and curled ears. That's the F1. Well, we could have told you that, right? We could have told them that. Now, one thing I did here that is not good is that I switched the order of these things. It's really a good idea to keep the order the same. So let's do that. Let's make sure I've got my little eraser here. Hard eraser. Alright, so I'll erase that. It's much better to say, so if we've got CU on the left and GG on the right, keep it the same. So this one is a homozygous black cat. I just did it because that's the way they wrote it. So homozygous black and CU, little cu. Black with curled ears. So this guy's gonna get this allele from this parent, get a little cu from this parent, and then get a big G from this parent and a little g from this parent. Tend to put the dominant one to the left. So it's heterozygous for the CU allele, and it's heterozygous for this one. CU is curled. So CU up here has a curled. So big CU is curled, big G is black. So that makes sense. So that's our F1. Now if we're gonna mate these guys, what are we gonna get in the F2? So we're gonna do a dihybrid cross. So now this guy is heterozygous for both, and we're gonna do a dihybrid cross. So CU Cu, big G, little g, cross to big Cu, little cu, big G, little g. Alright, so how are we going to analyze this? This is a dihybrid cross. We know that the alleles are independently assorting because it said that in the problem. So if we have two independent assorting alleles where it's a dihybrid, so this has the same form as big A, big B, little b, big A, big B, little b, same form, just using different letters. So that means that we can do this, where this guy's going to have a big Cu, and then we don't know what's going on here, and a big G, don't know what's going on here. This could be a big Cu, and either one, and then two little g's, little Cu, big G, blank, little Cu, little g, right? So that's, you can just memorize that. So because this has this form of a dihybrid cross, we know it's got to give us this. We'll see later that we can get some modifications of this sort of thing, but this is sort of a good starting point. So what are the phenotypes for these things? Curled and black, curled and gray, normal ears and black, and normal ears and gray. Alright, so it's important to put these phenotypes in. So, because if you just say 9 to 3 to 3 to 1, it's important that you say which one is 9 and which one is 3, etc. So that's that. So what other ways can we do it? So let's look at it again. Okay, so now just for the heck of it, let's do a Punnett square. So here, now, we're going to get either the big Cu allele or the little Cu allele. If we get the big Cu allele, we can get the big G, or we can get the little g. We get this little Cu allele with the big G, or the little Cu allele with the little g. Then we get the same thing here. So that should look somewhat familiar. If we had A's and B's, it would certainly be easy to fill this thing out. It's going to be a little hard to fit all this stuff in these boxes, and I don't really have the patience to fill out a whole Punnett square. But we'll get started. Big Cu, see, we can't even fit it in there. And big G, so we can do that. We can have a big Cu and another big Cu. Maybe if I do it like that, it'll fit. And then a big G and then a little g. Big Cu, little cu, big G, etc., etc., etc. Then all the way down here, we'll get one spot where we get these are little Cu's, little G. So there's only one of these. There's 16 boxes. So this is the 1/16. And then this one is like, let's see. So if we fill all of these out, let's go back here, we get this. You count all of those things up, there's 16 boxes. 1/16 looks like this, and if you look, you can count up 9 that look like this, 3 that look like this, 3 that look like this, and 1 that looks like this. Okay, so that's fine. We can do it that way. Let's do it another way, because it's good to do things lots of ways. This is the way I like to do it. Big Cu, little cu. Big G, little g. across to big Cu, little cu, big G, little g. Now what we're going to do is, what we have is a dihybrid cross, but a dihybrid cross is really just two monohybrid crosses done at the same time, in the same, just using the same organism. So what do we get if we do a monohybrid cross between big Cu, little cu, big Cu, little cu? It's the same as like big A, little a, cross to big A, little a. Same kind of thing. So what are we going to get? We'll get 3/4 big Cu and something else, and 1/4 little cu, little cu. If we do this guy by itself, we'll get 3/4. Let me move this over here a little bit. 3/4 big G, something else, 1/4 little g, something else. So what these represent are probabilities. This is, if we do this cross, how many of our cats, are they cats? I think they're cats. How many of these things are going to have curled ears? 3/4 of them. They have this genotype and the curled ear phenotype. 1/4 of them will have this. Of these 3/4 that have curled ears, how many of them are going to be black? Well, 3/4 of those will be black. So another way to think of it is, so this is the probability of being curled ears. This is the probability of being black. The probability of being both of these things is 3/4 times 3/4, or 9/16. If I can fit these in here. Curl, big G, little g. It's hard to fit in. So we're just multiplying this by this. Then we can multiply this by this, and we get 3/16 big Cu, little cu, little g, little g. And then if we take this and multiply it by this, we're going to get little cu, big G blank. And if we multiply these bottom two, this guy by this guy, we get 1/16 Cu, G, G. So this is called combined probability. And it's just using the simple probability rule that if we know there's a 3/4 probability of getting curled ears, 3/4 probability of getting black fur, the probability of getting both curled ears and black fur. Now actually this one, we're going to put a little line here, because this 3/4 Cu blank, this could be Cu, big Cu, little cu. Same here, so this has got to be a blank, because we don't know if it's big Cu, big Cu. This we know is little cu, but it has to have one big G. This has all little guys. Combined probabilities. We're multiplying this by this, then this by this, then this by this, then this by this. Alright, let's try it again. Let's just show you in general terms. Big A, big B, little b. Cross to big A, big B, little b. We know, so all we have to do is know what's going on with monohybrid crosses, and then we can figure everything else out. And then we know the different kinds of things we can get are this. You guys should really get used to writing this out, because this is the basis of a lot of things. So what's the probability of getting this? 9/16. What's the probability of getting these two guys together? 3/16. What's the probability of getting, here we'll do this, these two guys together? 3/16. And what's the probability of getting these two guys together? 1/16. Now, all of this depends on independent assortment. In fact, we use this type of cross to test for independent assortment. If we have two genes, A and B, and we want to know if they assort independently, we do this. And if we get a 9:3 to 3:1 ratio, that means they're assorting independently. And why that is because this combined probability method, what allows us to do this prediction and multiply this by this to give us this, that depends on these two things being independent of each other. So what I mean by that is that it's the multiplication rule of probability. What does that mean? So given any probabilities at all, doesn't matter what they are. Let's say the probability of something is 1/2. The probability of something else is 1/4. What's the probability of both of these things happening together? Well, as long as these two things are independent of each other, if this probability is going to occur no matter what, and this probability is going to occur no matter what, then in this case it would be 1/8. Because when you multiply fractions, you multiply the top to get 1, the bottom will get 8. Let's say we do, the classic example is you have if you flip a coin, you have a probability of heads equals 1/2. The probability of tails equals 1/2. So let's say we flip the coin twice. What's the probability of getting a head and then getting another head? That equals 1/2 times 1/2, assuming that the two coins are independent of each other. If you glue them onto a stick so that if you flip them in such a way that they always land the same way together, then they're not independent and you wouldn't get this probability. But if they're independent of each other, you get this. Let's say we flip it 3 times and we say heads, tails, or heads. In that order, we're going to get heads, then we're going to get tails, and then we're going to get heads. Well, the probability of getting the first head is 1/2. Probability of getting tails is 1/2. Probability of getting heads the third time is 1/2. And so that's 1/8 again. So that's just the multiplication rule of probability. We'll get into a little bit crazier probabilities. And I might as well show you that now. And we'll talk about it more a little bit later. But let's say what's the probability of getting, let's say, 1 head and 1 tail. What's the probability of that? With 2 different flips, what's the probability of getting 1 head and 1 tail? Well, there's 2 ways to get this. You can get the first one could be a head, and the second one could be a tail, or the first one could be a tail, and the second one could be a head. Both of those satisfy just that we're going to get this combination. Well, we know the probability of this is 1/4 because it's 1/2 times 1/2 gives you 1/4. We know that the probability of getting this option is 1/2 times 1/2 is 1/4. So if you're saying what's probably getting a head and a tail, you multiply them together. If the probability of getting a tail and a head is probably getting them both at the same time, getting this and this, you multiply them together. But now, in order to satisfy this question of what's the probability of getting 1 head and 1 tail regardless of the order, I'm going to put that in there, is that the probability of getting this particular case is 1/4 and the probability of getting this is 1/4. But either one of these satisfies the condition. So that's an or. What's the probability of getting this or this? Then you add them together. So this is 2/4 equals 1/2. So that's the addition rule. Of probability. So if we say A, you want the probability of A and B, then you multiply. If you want the probability of A or B, A and B just being any probabilities, then you add them together. So I just wanted to introduce these notions of probability. It'll get a little bit more complicated, and so I'll just give you a little heads up that when we start considering all possible combinations, one of the next things coming up, so look at this in your book and we'll do some problems, something called the binomial expansion. So that's coming up. I don't want to go into it right now, but it's pretty cool actually. You can use this to say, so if I have 6 kids, what's the probability that 4 of them will be girls and 2 of them will be boys? And all it really does is it takes in all the different orders and all the different combinations that are possible. So look that up and try to figure it out. If you're not real comfortable with math, it'll be a little weird at first, but it's kind of cool once you get the hang of it. So, all right, that's it for now.